This a question involving capacitor and resistor connected to DC circuit. We are asked to find total resistance of the network, potential difference across each resistor and the capacitor, charge and energy stored in the capacitor, assuming steady state. That's a normal question with DC circuit, assuming steady state. So steady state meaning when you connect a capacitor to cell, the capacitor gets charged, the plate connected to positive terminal become plus and the negative terminal become minus. Once the capacitor is fully charged, then no current flows through the capacitor. Initially, for a fraction of a second, which happens very fast, the capacitor becomes charged. That charging time, current will flow through the capacitor branch. Once the capacitor is fully charged, then no current flows through the capacitor. There will be charge stored inside the capacitor. There will be potential difference across the capacitor because V equal to Q by C. If there is a charge, there will be a potential difference. Even energy will be stored inside the capacitor, half C square. But no current continuously flow through the capacitor, across the capacitor. Current will be zero, but charge, potential difference, energy, all will be present across the capacitor. So when you find total resistance, we can neglect the capacitor because no current flows through the branch, then there is no meaning of resistance. The resistance to be counted when the current is flowing. There are so many regions when current is not flowing, we don't count that, all part of the circuit. So since no current passes through the capacitor in steady state in fully charged state, then you can neglect the branch of the capacitor, because if capacitor don't have any current, automatically this branch CEF, which is 3 ohm in series with the capacitor, even don't have any current. The first point, what's the meaning of steady state? A capacitor fully charged will have charge stored inside, potential difference across the plate, energy stored, but once it is fully charged, no current passes through the capacitor branch. Now, when we apply this concept, when no current flows through the capacitor once fully charged in a DC circuit only can fully charge and remain like that. AC circuit, the plus minus will change, the capacitor will charge and discharge. That's a different case that will be in chapter number 6, 7 AC, alternating current. But here this is DC. DC can maintain the potential difference constant once fully charged, no current flows through this. So then you can remove or imagine the CEF branch to be removed when you find the total resistance and current through the network. But when you find potential difference in different branches, you cannot neglect CE because there will be a potential difference in the across the capacitor. Even resistor can be neglected because when current is zero, the potential difference across the resistor is I into R. For a resistor, V equal to I into R. Since I is 0 through EF, there won't be any potential difference across the resistor, whether fully charged or during charging time there will be, but that we are not interested here. During fully charged state, there will be potential difference across the capacitor, but no potential difference across the resistor because V equal to I into R, I is 0. Capacitor potential is V equal to Q by C. Q is there, C is there, so we have potential. Now we are redrawing the diagram by removing CEF, imagining CEF to be removed for finding the total resistance, current and potential difference across the rest of the branch. will go. Now you can see this B, C, D. B to C, C to D, there is no branching. It's a single straight line. Straight line means single path, like without any branching. So this path without any branching will show series combination. Same charge flows through, same current flows through this. So these two are in series. The total resistance can be 6 ohm. Now you can replace B, C, D as a 6 ohm between these 2 points, the 6 ohm. That 6 ohm will be parallel to 3 ohm. So this 6 ohm is a replacement for 3 and 3 in series. Now the effective combination of these two parallel resistors, we can use a formula 1 by R equal to 1 by R1 plus 1 by R2. If you take LCM on the right side, it will be R1 plus R2 by R1 R2. If you take reciprocal, it will be R1 R2 by R1 plus R2. The parallel combination resistance is directly product of the resistor by sum of the resistance. Rp equal to R1 R2 by R1 plus R2. The rule is 1 by R equal to 1 by R1 plus 1 by R2. But if we take LCM on the right side and take reciprocal, it will be Rp equal to R1 R2 by R1 plus R2. 6 into 3 by 6 plus 3. The total resistance of this parallel combination will be 2 ohms. Now we can replace 6 and 3 by a single resistance between that. So that will be 2 ohms. Now that resistance becomes 2 ohm, that is in series with 3 ohm. The total resistance will be 3 plus 2, 5 ohm. So the whole resistance of the network is just 5 ohm. That's the first part of the question, total resistance of the network. We don't include EF because no current flows through EF. Now we are supposed to find current potential difference across resistor and capacitor. We got the total resistance, we got the total voltage, we can find the total current. Total current will be total voltage 15 by the total resistance 5. So 15 by 5, 3 ampere. So 3 ampere starts from the cell, from positive and go to the circuit like this. Now it's a very simple circuit. We can use Ohm's law to find the potential difference across AB. I into R, 3 into 2, 3 ampere into 2, 6 volt. Same current flows through DF also. So 3 ampere into 3 ohm will be 9 volt. So AD will be 6 volt, DF will be 9 volt. DF 9 volt means the potential difference across this 3 ohm will be 9 volt. Now if you look back from here, so these are the values for 9 volt and 6 volt for AD and DF. Now if you look back this 2 ohm is parallel combination of AD and the 6 ohm, which is B, C, D. In parallel combination, the voltage remains same. That means voltage across 6 ohm. The 6 ohm, which is B, C, D, have the same voltage of this AD, which is 6 volt. So now this is 6 volt. So you can find current through that. 6 volt here, 6 volt here. So the current through 6 ohm will be 6 volt potential difference by 6 ohm, that will be 1 ampere. So 1 ampere current flows through the 6 ohm, only 6 ohm. And this 6 ohm, which is BCD, if you check, that is series combination of BC and CD, the 2, 3 ohms. Since the 6 ohm carry 1 ampere current, the series combination which gives 6 ohm, 3 and 3, BC and CD. This also will have 1 ampere current, same current. In series, current remains the same. Both 3 ohms will have same current, 1 ampere. So they are in series. Now if you know the current through this, you can find potential difference across BC and CD. Just Ohm's law. Current is 1 ampere, 3 ohms, so 1 into 3, 3 volt. CD also same 1 ampere into 3, 3 volt. So potential difference across BC and CD will be 3 volt each. So we got potential difference across this 3 ohm. We got across this 3 ohm, which is 6 volt. We got for BC and CT. Now for the capacitor. For the capacitor, we apply the Kirchhoff's voltage law for the outermost loop, A, B, C, E, F, cell back to A. You can apply any closed loop, it will work, but this is a simple case because only one resistor, one capacitor. This resistor is not involved because it don't have a potential difference, then only the cell. There are cases we have circuits here. Anyone you can use. We will take the outer loop. Only two components along with the cell. When you apply that, the current is starting from 15 ohm. You divide into 2 here. Current will go from B to C, then down. No current flows through this, no current flows through this. Then this current will go down from C to D, then A to D, both will join and go to 3 ohm and come back. So when you apply the rule is for a closed loop, the total potential difference is 0. For a closed loop, the total potential difference is 0. When you find the potential difference, we have to find the sign of the potential difference across each component. When current is entering, that is plus. When the current is leaving, that's minus. Or current flows from higher potential to lower potential. So for 3 ohm, the current flows from B to C. That means B is plus and the end is minus for 3 ohm. If you take the capacitor, the left end of the capacitor is connected to the positive terminal of the cell. That becomes positive polarity, and the right end is connected to the negative terminal. The right end of the capacitor becomes negative. For the resistor, the B side is positive, the C side is negative because current flow from higher plus to lower potential minus. For capacitor, the left end is connected to the positive polarity of the cell, that becomes plus, and the right side becomes minus. Now resistor not to be counted because current is 0 in steady state and potential difference is 0. When you apply the rule, 15 volt is a cell. Here we already calculated the potential difference as 1 into 3 as 3 volts across DC. The sign of potential difference when you apply the voltage law is the sign from the terminal you leave the resistor. For example, if you go from B to C, this is 3 volt. Since you are leaving from the negative terminal from the resistor, it's minus 3 volt. If you go from the left to right to the cell, leaving from the positive terminal, that is plus 15 volt. So the total potential difference is 0 for a closed loop. The sign convention, from which terminal you leave that device, that is the sign of potential difference. For cell, no issue. We already know the longer line is plus, the other one is minus. If you take from left to right, it will be minus 15 volt. If you take from right to left, it will be plus 15 volt. Because you give from positive terminal on the second case and negative terminal on the first case. For resistor, the current flow will decide plus minus. The current is going from B to C. Current always flow from positive to negative, higher potential, lower potential. So B is plus, C is minus. If you go from B to C, it will be minus 3 volts. If you go from C to B, it will be plus 3 volts. For capacitor, the left is plus, right is minus. We are applying the law. From A to B, there is no device. From B to C, is 3 volt here. Since you are leaving from the negative terminal, it's minus 3 volt. For capacitor, you are leaving from E, which is negative. We don't know the value, you are writing DC. So minus 3 minus E of the capacitor, then no potential difference here. We are going to the plus from minus, cell from minus to plus, plus 15 volt. So minus 3 minus V of the capacitor plus 15 equal to 0. Now you can leave VC to the right side. So 15 minus 3 will be left side, VC on the right side. So VC will be 15 minus 3, 12 volt. You got the voltage across the capacitor, 12 volt. Now you can find the charge. Charge is just 2 times of C. 2 equal to C times of V. So Q, C is 3 microfarad, 3 into 10 to the minus 6 farad, V is 12 volt. So 3 into 12, 36, 10 to the minus 6 So 36 into 10 raised to minus 6 coulomb, 36 microcoulomb is the charge stored in the capacitor. So energy stored in the capacitor you can use half CV square. So half C is again 3 into 10 raised to minus 6, the voltage is 12. So 12, 144, and 44 by 3, 72, 3 into 72, 216. So 216 into 10 raised to minus 6 joules. That's the energy stored in the capacitor. So if you take 2 points back, 216 can be 2.16 into 10 raised to 2. So 10 raised to 2, 10 raised to minus 6 becomes 10 raised to minus 4. So the total energy stored is 10 raised to minus 4. They asked for total resistance. The total resistance is 5 ohm total resistance. Then they are asking the potential difference across each element. The other potential difference among them, charge and the signs are not clear. I'll just show you once more. Like the 3 ampere starts from here. The same 3 ampere flows through these two resistors. That's why 3 into 2, 6 volts, 3 into 2, 9 volts. And the current will reach here. This is 6 volts, this also 6 volts, both are 6 volts. So that will give you a current of 6 by 6, 1 ampere here, 6 by 3, 2 ampere here. You don't want that, but just for understanding. Then this 1 and 2 will join again as 3 volts. That's what we have already, 3 ampere through 9 volts. So again we reach here, this is the 3 ampere. That will be can split into 2 ampere because 6 volts by 3 ohms. This will flow as 1 ampere because 6 by 6 is 1 ampere. When this 1 ampere is flowing from B to C, the current always moves from higher potential to lower potential. Then this will be plus minus. We are not taking that for the loop, that's not marked. This will be still same as 1 ampere. So 1 and 2 again join as 3 ampere. So go to the top, this is again 3 ampere. This will be 2 ampere. This is 1 ampere. So this potential difference is 3 volts. This is 1 into 3 and this is plus minus because current flows from B to C. For capacitor is connected left side to the positive terminal, this is plus. Right side to the negative, this is minus. Now the potential difference of the capacitor we don't know, we just mark it as VC, we find. And here current is 0, so the potential difference is also 0 for that resistance. Now when you apply the loop rule, we are going from A to B, B to C. A to B nothing, B to C have 3 volt, minus 3 volt. We are exiting from minus 3 volt. That's why minus 3 volt. For a capacitor, we are exiting from minus. That's why minus VC. We go that way and go from the cell to the left. We are exiting from the positive cell. Let's say plus 15. So that's how we find the potential difference across the capacitor. So basically step 1, when capacitor is given with a series of resistant DC circuit, first imagine the capacitor to be absent. Then you solve the remaining network either using simple parallel series combinations that allow you to. Otherwise, you have to use Kirchhoff's voltage rule and junction rule to find current and voltage across the capacitor. And after finding the current and voltage across each device, you come back to the normal setup where the capacitor is already present. Then apply Kirchhoff's voltage rule through any one loop which involves the capacitor. Any one loop will work. Using that, you can find voltage across the capacitor. And keep in mind, if there is any device, resistor in series with the capacitor, just series with the capacitor, that will not have a current, that will not have a potential difference. That's the basic rule for solving circuit with resistor, capacitor connected to DC.